So webinar, today's webinar is about physics equations and dimensional analysis. So we're going to be talking about physics equations. We're going to look at all the physics equations you need to know for the GAMSAT. It's on the website. You have the URL. There's a couple of things that I do want to mention to have the proper perspective. One is that you will hear a student who will say that they never memorize an equation for the GAMSAT. And this is completely realistic, okay? Because if you have a science background and if you have a strong reasoning skills, then there are very, very, very few equations that you actually need to memorize. I mean, Ohm's law is the first that comes to mind, but there are very few equations you need to memorize because of um, strong reasoning skills and understanding the basis of a lot of these relationships. Then it becomes easier. So I want to make sure that you understand. I'm not simply saying that memorizing equations will be the solution. It's just that sometimes by having certain equations at the tip of your tongue, easy, to put out during the exam, it makes it a little faster, more efficient, and of course, time is quite a challenge in terms of finishing the different sections of the GAMSAT. So I want you to have that perspective. Also, I also want to say that if you have no science background whatsoever and you haven't done any review, you haven't looked through any of the book or the videos or anything, then of course, this webinar will be extraordinarily challenging, and you won't be able to get very much out of it. There will be a few little things that you'll be able to get and retain, but hopefully you've done a little bit of review, so some of this uh, will resonate. And even if it doesn't, there's going to be still some things that we'll be looking at in terms of some practice problems that hopefully you can start to get some understanding of some of the relationships. And at the end of this, we will be looking at some, a couple of sort of GAMSAT level questions that require dimensional analysis. There are many different types of questions that require it, but we will be at least looking at some of that. Okay, so let's start. So I'm hoping you have the web page. You see where we're going with this. So okay, so let me just get a pointer here. So momentum and impulse. So momentum is mass times velocity. So this is a very fundamental definition, for momentum, which is mass times velocity, and you know that velocity is a vector. So velocity has a number and a direction, and because it's being multiplied by mass, which is a scalar quantity, mass has no direction, it only has a number. So it's the number of kilograms, for example, in SI unit. And this gives us a vector, which is momentum. So that's M for momentum. And that means that momentum has a direction. And that means that if the two things that strike each other are moving off in different angles, then we have a new issue, which is it has to be resolved into their different components, x and y components. And that's where you have to use the functions sine theta and cosine theta, which we'll look at in a moment. But just to keep in mind that momentum is a vector. And in bold, when in the left column in bold, those are the sections, if you happen to have the gold standard GAMSAT textbook, those are the sections in the book where you can read up more about these equations. And if you don't, of course, you could just Google it, and you will have the information about these equations. One thing that I do want to underline, especially for students with non-science backgrounds, is that don't get attached to what the letters represent. Here I have capital M for momentum. Some books will use a Greek letter for momentum, and you will see change in momentum in a moment. We will see might be symbolized with a capital I for impulse, but it could be so many other things. And even for the next equation we're looking at, which is going to be conservation of energy, even those terms can be used in so many different ways. Don't get attached to letters. Don't get attached to symbols that represent ideas. The important thing is that you learn the idea. It's not about the equation. It's about the relationships behind these. And by the way, sometimes on the GAMSAT, what they'll do is they'll use atypical ways to represent an equation. So sometimes they will give you the equation during the exam, but they will represent it in an atypical way. And just to see whether or not you can roll with the punches and just be able to use your understanding and not get confused by the different letters or representations that they may have. So that's very important for you to understand, because I know students who are learning science for the first time, they get frustrated when they see equations written in different ways in different textbooks, or sometimes different ways in the same textbook. But that's not relevant. It's the idea. Okay, so conservation of energy. Conservation of energy is used in almost every one of the ACER practice materials. And so that's how important of a concept it is. And it's easy to state, which is that the total energy is equal to the kinetic energy plus the potential energy. And so it's an amazing concept because it could be used in so many different things. A ball is falling down from one level to another. The total energy of the ball is constant, the total kinetic and potential energy. But that's just a ball. But then you get something that looks so different, like something on a string, or a person, say, swinging on a swing, or a roller coaster ride, where the roller coaster is going up and down and spinning and turning. There again, as long as friction is not an issue, which is normally the case in introductory level science, but sometimes it isn't, but normally is the case, then you can use conservation of energy, and in that kinetic energy plus potential energy, the total energy. Actually, of course, even if friction does occur, the total energy is still constant, but there is an additional factor which is not presented in the equation that I'm showing you. And then the relationship between work and power. So one expression that you can remember is that power is the rate of work. So you see it's a change of work over the change in time. So another way of expressing that is that power is the rate of work. The expression rate in science is often used when something is occurring per unit time. So that's a very important equation. And I just, to review the units here, what is the unit for energy in the SI system? It's extremely important that you're very comfortable with all the units in the SI system. Yes, so the unit energy is a joule, and the unit for power is what? Yes, I said what, not watt. The unit for power is a watt, and so we have power in units, which is watt, is change in work, and change in work has the same unit as energy. So the change in work is joules per second. So a watt is a joule per second, and that's very important. I would say, probably every second exam, you're going to use that small fact in order to solve a problem. It won't be the only. It won't be the only part of the solution, but it'll be part of the solution. Next is the current, and current, you can see here, is the charge over unit time. Current is in units of amperes or amps, and charge, Q, is in coulombs, and that's per unit time. And in the SI system, time is seconds. So that means that amps is equal to coulombs per second in terms of units. And that's, obviously important to know. And hopefully you would be comfortable with this because the classic analogy for current, current is moving through a wire. The classic analogy is water going through a river. Okay, so water in a river. And of course, when you think of water in a river, you think of currents as it's moving through it, and you think that the water is moving over per unit time, and that's current. How fast is the current? How fast is it moving per unit time? How much volume, for example, is moving per unit time? That's current in the context of a river. Uh, Volume per unit time is literally a flow uh, in context of a river, and in context of current in a wire, you can think of a charge moving per unit time, and that's the current moving or flowing in the wire. And resistors and capacitors can be in can be connected either in series or in parallel. In series means it's one after the other, and in parallel means that it sort of looks in parallel. Say it any other way, but let me see if I can. Okay, so something like that is resistors in series. Um, the capacitor is symbolized by two parallel lines which are equal in size. So two parallel lines equal in size is a capacitor. Whoa. So one after another means in series, of course, and parallel is where you have junctions, which I drew for the resistor, but which I will not attempt for the capacitor. It would look exactly like what I did for uh, the resistors, but it would have been much nicer, I'm sure. But the idea is that the resistor simply would be exchanged for capacitors, which are parallel lines of equal size, because parallel lines of unequal size represent a battery. Now, the purpose of a resistor is to resist the movement of current, of course. That's why it's called a resistor. And if you want to calculate the total or equivalent resistance across these resistors, then when they are in series, you just add the resistances, R1 plus R2. The SI unit for resistance is the ohm. And here we have resistors in parallel, as you can see, because it looks like they're in parallel. They have two junctions, two areas in which they are connected. And in order to get the total resistance across these resistors, it's 1 over R1 plus 1 over R2, etc. So that's the equivalent or total resistance. And so you see here that the equations for the equivalent resistance for uh, capacitors is, if it's easier for you to remember, it's opposite the way the equations work as to the way that the equations work for resistors. So, so it's the reciprocal here, and then here you just add the capacitor for each. Then, when you're trying to solve circuit problems, and circuit problems regularly come up for the GAMSAT, and very helpful is to know Kirchhoff's two laws that can solve basically any circuit that they can possibly give you. And the first law is that the sum of current is equal to 0 at a junction, and that means that you take a look at the junction. A junction is where any wire comes together, and you can look at all the current coming into that junction uh, as positive. Okay, this is random. This is arbitrary, I should say, as long as you are consistent. But you can say all the current coming in is positive and all the current leaving is negative. And so by doing that, you sum the current, and it would be equal to 0 at any junction. And also, in any loop, which is any enclosed area of wire. Would be a loop, goes in a circle, so it's a loop. The change in voltage is equal to 0 in any loop in there. Okay, torque forces. Torque forces also comes up very regularly for the GAMSAT, and there are basically two very important rules that help you to solve any torque force problem. Just like there's two Kirchhoff's laws, there's two rules. The two rules for torque force problems is translational equilibrium and rotational equilibrium. In translational equilibrium, which sort of means just going in one direction, sort of, so that equilibrium means that the thing is not accelerating. Okay, so it's either moving at constant velocity or it's not moving at all. And normally, the way it is for the GAMSAT is that it's not moving at all. So it's often they'll have a person on a bed or a stretcher or something like that, and so they're not moving, and then you have to look at the different forces that they're experiencing at that point. So the sum of forces in the x direction is equal to 0. Sum of forces in the y direction is equal to 0. The sum of forces in the z direction is equal to 0, likewise, as long as it's in equilibrium. So that's called translational equilibrium. And in rotational equilibrium, this is where the sum of the clockwise torque forces is equal to the sum of the counterclockwise torque forces. That's rotational equilibrium. That's rotational is turning, so that's turning equilibrium. It's not rotating at acceleration. So what is these clockwise torque forces? So this is what it is. This is the breakdown of what a torque force is, and that is it's the force applied times the perpendicular distance from the pivot point. The pivot point is the point about which something turns, and so you calculate the distance to that pivot point, and you multiply it by the force. And that's the counterclockwise torque force, for example, which you can take as positive. You can. It's up to you. Again, it's arbitrary. But then the opposite would be negative. So if you have the counterclockwise, for example, being positive, then the clockwise torque force, but that would be arbitrary. So next on our list is force is equal to ma, which is one of the fundamental equations of physics, which is Newton's second law. And basically, it's stating that if you have a net force, then you must have acceleration. So anytime there is a net force on any object, there must be acceleration. And that is that's the main idea here. So sum of forces equals to mass times acceleration. Force, of course, is in Newton. And we know what a Newton is in terms of fundamental units because mass is in kilograms in the SI unit, and acceleration must be in meters per second squared. So force, newtons, must be equal to kilogram meter per second squared. And you're expected to be able to go back and forth with these different types of units. And here's weight, and weight is a force. So that means weight is indeed in Newton. And the weight can be given by mg, which is mass times gravity. Pressure. Pressure is force per unit area, and you can imagine, and if ever you have problems and you forget and you're during the exam, just apply pressure to the table in front of you or to your exam paper, and you will notice as you're applying pressure that you are indeed applying a force over a specific unit area, and that is the definition of pressure. And this is another equation or concept that comes up very regularly on the exam, sometimes multiple times on the same exam. The importance that you know what pressure is and that you also know the unit for pressure. And the SI unit for pressure is what? What is the SI unit for pressure? Because it is definitely expected that you know. Yes, it's the Pascal. Okay, so buoyant force. The buoyant force, well, first of all, before that, of course, it's important that you remember that density is mass per unit volume. That's important. And of course, in the SI system, that means kilogram per meter cubed. And for some of you, may not be comfortable or used to seeing kilogram per meter cubed, because that's not usually going to be used in any science labs. But that is the SI system, and it is expected that you know that and can work with that. Now, for the buoyant force, the buoyant force is given by the volume, that's V. That is not a P, it's rho, which is the Greek letter rho, which stands for density, which is mass per volume, and G, which is gravity, and that's equal to the weight. So that's the buoyant force. Optics. There are a number of very important equations for optics. One of the most important ones, in my opinion, is this simple one, which most people either don't remember or don't think is important, which is that the magnification is equal to negative I over O. So that's magnification is equal to negative I over O. I is the image distance, O is the object distance. And the importance of the equation is a couple of things. One is that it helps you to identify if the object is reduced in size or enlarged. If it's enlarged, the absolute value will be greater than 1. And if it's reduced in size, the magnification will be less than 1. It will be a fraction, which makes sense. If it's a fraction, then it's getting smaller. So and the other thing about the magnification, which is very helpful, is that if the magnification is positive, then the image is erect, and if the magnification is negative, then the image is inverted. And having questions about enlarged, diminished, inverted, or erect, those also come up regularly for the exam. Okay, here's some equations that also come up one way or the other regularly because, well, first of all, let me describe the equation. So this is Newton's law of gravity, and this is Coulomb's law. Newton's law of gravity, uh, lets us know that the force of gravity is given by kg, which is the gravitational constant, times m1, m2, which are the two masses involved, over r squared. And r is not the radius. It doesn't stand for radius. R stands for the distance between the center of masses of the two masses. So any two objects have some force of gravity between them. So there's a force of gravity obviously between you and the planet Earth, but there's also a force of gravity between you and the chair, you and the table, you and your computer. There are these forces of gravity. Of course, the gravitational force between you and your computer is extraordinarily low, and it takes something as big and massive as the planet Earth to make gravity so important as to, let's say, keep us on the planet. So gravity is actually one of the weakest forces in nature. Then over here we have Coulomb's law, much more powerful force, which is the electric field force. And the force in the field is given by K, which is Coulomb's constant. And you can just imagine Coulomb's constant is way greater than the gravitational constant. And if Coulomb's constant type Q1, Q2, which are the 2-point charges involved, over r squared. And r is the distance between the 2-point charges. And then this gives you the force. And just a quick question here about magnification. So positive magnification is erect, negative is inverted. So that should be relatively easy to remember. It's a bit intuitive, but that's why the equation has that negative sign in it, so that the result becomes intuitive. Okay, so now one of the reasons why this is so important, these equations are so important, is because Acer likes to sort of ask questions where you double the mass, what's going to happen to the force of gravity? So we see here that if you double one mass, then the force of gravity will be doubled. If you double both masses, then you have 2 times 2, that's 4. So then the force of gravity will be 4 times. The other type of question they like to ask is what happens if you double the distance between or triple the distance between. You can see that it's an inverse square law. So if you double the distance, then it's 2r squared, and then the 2 is squared, so that's 4. So if you double the distance, you quarter the force. If you triple the distance, you get 1/9 of the force. So those are typical relations that they love to ask on the exam. Inverse square laws, inverse square root laws, which this is not, but they can present one to you, and direct relationships. Force and mass have a direct relationship here, and so they can ask you to double, triple, whatever, and see how you can manipulate the equation. Next, we have, very famous, as I said, if you have to make a shorter list, you definitely still keep this on the shorter list, which is Ohm's law, which is voltage is equal to current times resistance. So voltage is in units of volts, current is in amps or amperes, which we already saw, and R resistance is in ohms. And then we have P is equal to IV. P is the power, we already said in watts. I is current, and V is the voltage. So those are common relations. And then these are super basic, probably not even grade 12, probably grade 10 physics. So velocity is the change in displacement over time. So delta t over delta t, or the rate of change, the rate of displacement, and that the average velocity is the change in velocity over the change in time. And both of these equations, I know that the red booklet is not the most difficult of Acer's materials, but both of those equations are worn out during the red booklet. So they are important. Next, v. These are for waves. This is v. The velocity of a wave is equal to lambda, which is the wavelength, time f, the frequency. And again, some books will use a Greek letter, mu, for frequency, but it's not important. And energy of a wave is given by Planck's constant times f, the frequency of a wave. And this is a reminder of the relationship between frequency and period. And sometimes this will come up. And they are the inversion of each other. So frequency, how often something occurs, is the opposite of the period, which is 1 over t. And this is also helpful to know. We'll see some series of equations in a moment, but to see that the frequency, how the frequency is related to the energy only through a constant. That's important because if the energy is not changing, the frequency is not changing. So if they ask a question about velocity, and if the velocity goes up or down depending on the wavelength, if you know that the frequency is unchanged, then it means that double the wavelength, double the velocity. That's the kind of thinking that goes on. And this idea of the frequency not changing, we'll see the important case for you to know because it comes up regularly. That'll come up in a moment. And we talked about the conservation of energy already, and here is the breakdown, which you are expected to know, that the kinetic energy is 1/2 mv squared in joules, and yes, the units of wavelength is still meters in the SI system. And if they ever use other units, and don't forget that they can and will use units that are not SI systems, but the only units you're supposed to know are SI system units, but they can use other systems, but they'll have to give you a conversion factor. So for kinetic energy, 1/2 mv squared, mass times velocity squared, and potential energy is mgh, mass times gravity times height. Okay, now, see, these are the types of equations that some people don't like to memorize because they feel that, well, you should already have an understanding of these equations, which is fine. And so, but I still suggest that you know these equations. So, that's up to you. So these are the equations of translational motion. And these equations, you need to know them, okay? It's helpful if you also understand these equations graphically. And, of course, we don't have the time for that, but one of the videos that I do for the Acer Red booklet, which is on YouTube in physics, so when you get to that, you'll see it. I go over sort of the graphic interpretation of how these equations uh, develop. So this is displacement, which is x, and so xo is the original position. O subscript usually means original, and subscript F final. So the original position, VOT, which is velocity, the original velocity times time, plus 1/2 AT squared, 1/2 acceleration times time squared. So that's the displacement. And the final velocity squared is the original velocity squared plus 2ax. A is the acceleration, x is the displacement, and original velocity and final velocity. And here is the final velocity, original velocity plus acceleration times time. And just as a reminder, hopefully you know already, or you're going to go through it in your notes, but you know that velocity is the slope of a displacement versus time graph. Hopefully you don't need to really memorize that, but you know that based on your understanding of the linear equation, y is equal to mx plus b. And also acceleration is the slope of a velocity versus time graph, again for the same reason. And hopefully also you know that the displacement is the area under the curve for the velocity versus time graph. And we're going to see in a moment that the area under the curve for a force versus time graph is called the impulse or the change in momentum. We'll see that in a second, and we'll see why. And 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 we'll look at the area in the graph for work as well in just a moment. So for the spring force it's is equal to negative kx, where k is the spring constant and x is the displacement. The work is kx squared over 2. I must say, it'd be pretty unusual for Acer to require you to know that offhand, but it's pretty easy to remember anyway. But refraction, this one is, I would say, shocking. I would never guess that, that Acer would require you to know this, but they do, and you'll see this as you go through the booklets. So I think it's easier to remember this one first, which is the index of refraction is equal to c. C is the speed of light in a vacuum, and it's a constant, and over v, and v is the speed of light in the medium in question, and which will always be slower, okay? Because if it's not in a vacuum where there are no particles, an evacuated space, then it's going to be slower. So v will be a slower number, and because it's slower, uh, it means that the index of refraction will be above 1. So that's why you get an index of refraction of 1.3 or 1.5 as you go from air to glass, etc. So not that you need to memorize indices of refraction, but need to know that it's going to be over 1, and this is the reason why. But it also lets you know that there's an inverse relationship between the index of refraction and the velocity. So now we can see why in this equation you have sine theta 1 over sine theta 2, you have v1 over v2, okay, and then you have n2 over n1. Why? Because of the inverse relationship between the index of refraction and the velocity. And then you have lambda 1 over lambda 2. And knowing this equation, as you will see when you go through the Acer's Blue booklet, uh, is necessary, to solve the problem. So, and for those of you who remember Snell's law, you'll see Snell's law is embedded in this equation because Snell's law is n1 sine theta 1 is equal to n2 sine theta 2, and you can see that that's the meaning of part of this equation. but this embodies more information. And notice that the frequency is not here. And the frequency is not there for good reason, and that's because it's constant. And that is also an important point. So when you go from one medium to another medium, air to water, water to air, space to air, whatever, um, the frequency remains constant, but the wavelength changes, velocity changes, and obviously the index of refraction changes as you change the media. Next, pressure. So this is pressure in a fluid, and it's usually called static situation because we're not talking about fluids that are flowing and actually moving. So when you look at the change in pressure as you go from one point in a fluid to another, which means from one level in the water to another level in water, or even in air, because air is also a fluid. So you go from one level to another level. The change in pressure as you go from one to another is equal to density of the fluid, gravity, times change in height or depth. As you go deeper and deeper, of course, the pressure would increase. Then here, atomic physics, if the number of half-lives n are known, we can calculate the percentage of a pure radioactive sample left after undergoing decay, since the fraction remaining is 1/2 to the power of n. So 1/2 to the power of n, where n is equal to the number of half-lives. And you would notice, I know this doesn't have to do with biology, obviously, but this equation is very similar to the equation for bacterial doubling time, which you're expected to be familiar with. And that equation is 2 to the power of n, just because it's bacteria doubling time, not half-life, and where n is the number of times, the number of doubling times, just like here is n the number of half-life. Okay, so here's some equations that are occasionally helpful for theoretical things. Here's the frictional force, which is equal to mu n, where mu is the coefficient of friction and n is the normal force. And it's useful to know that the coefficient of kinetic friction is always less than the coefficient of static friction. And of course, you should have familiarity with this concept because if you have something heavy you need to move, it's always more difficult to get it moving rather than to keep it moving. So the static friction, not moving, is greater than kinetic friction when something is moving. Then momentum and impulse. So the impulse is equal to the change in momentum, and that is equal to force delta t, force times the change in time. And now you can understand, I hope, why I mentioned before that impulse is equal to the area under a force versus time graph. Because if you have force versus time, that's like x times y. Actually, it would be y times x. But, it'd be one axis times the other axis. Typically, it's typically time is when something is moving. then momentum and impulse. So the impulse is equal to the change in momentum, and that is equal to force delta t, force times the change in time. And now you can understand, I hope, why I mentioned before that impulse is equal to the area under a force versus time graph. Because if you have force versus time, that's like x times y. No, actually, it would be just y times x. But, it'd be one axis times the other axis. Typically, it's typically time is on the x-axis. It doesn't need to be. And then you would get like a box, and then the area under it would be the impulse, according to this equation. Next is the electric force, and electric force is equal to QE, just like the Newton's second law is force is equal to mass times acceleration. This is very similar, where the electric force, the force in an electric field, because Newton's law is about the force in a gravitational field. This is in an electric field is equal to Q, the charge in an electric field, times E, the electric field. So just like MA, where A is the acceleration in the gravitational field, this is the acceleration in an electric field. So it's QE. In optics, this is the equation. Now the reason, typically, this equation will be given on the exam. They might use different symbols, but typically they'll give this equation, and it's 1 over I plus 1 over O is equal to 1 over F, which is equal to 2 over R, which is the power of the lens. So 1 over I is the image distance, as I said before. 1 over O is the object distance. 1 over F is the focal length of the lens. And 2 over R is the radius of curvature of the lens. So you can see immediately, because 1 over F is equal to 2 over R, you can see that the radius of curvature is twice the focal length. Just going to extend this. Okay, so that's the power line. So specific gravity is a very important concept for the GAMSAT. I would say it comes up quite regularly. Easy and very straightforward concept. And that is the density of a substance over the density of water is specific gravity. So of course, water would have a specific gravity equal to 1 because the density of itself over itself makes 1. So, but then, if you have something that's lighter than water, then the specific gravity would be less than 1. So, and now for the density of water, which also you would be expected to know, it's pretty basic, that the density of water is 1 gram per centimeter cubed, which is the same thing as saying 1 gram per cubic centimeter, or cc, which is the same thing as saying 1 gram per milliliter. And this is the same thing as saying 1,000 kilograms per meter cubed. And although you're not as used to seeing kilograms per meter cubed, as I mentioned before, this is the SI unit, and this is what you should be expecting for the exam. So you need to be sure to have that flexibility. And then note here that the specific gravity is equivalent to the fraction of the height of a buoyant object below the surface of the fluid. So the specific gravity is equivalent to the fraction of the height of a buoyant object below the surface of the fluid. So this is what it means. If you, it's easier to think of it this way. If you have a specific gravity of 1, it means you have the same density of water, and that means 100% of you would be below the surface of water if you were put in water. And if you had a specific gravity of 0.9, which is close to 1, but a little less, if it's a solid object, you put it in water, it means that 90% of that object will be below the surface of the water. And if you have a specific gravity, likewise, of 0.3, it means that 30% of the object, 30% of the height of the object will be below the surface of the water. Okay. Okay, so let's do a few practice problems before we finish off. So if you can answer this question, please. Yeah, please try to answer the question. You're looking at the entire question. The entire question is m is mass, a is acceleration, t is time, ma squared times t is equivalent to which of the following units? I'll give you another moment. So it looks like most people have chosen answer A. Now, if I'm looking at this in the exam, of course, if you look at the answer choices, they all have watts in it. And then, in the, I'm going to just keep that in mind. Now I'm going to try to break up this uh, MA squared. I don't know what A squared means, okay? I, I, I don't see A squared, acceleration squared very often, so it makes me want to break that up. So I'm going to break up that A squared into bigger. Into something that I can recognize. So this is what I'm going to do. Okay, so I just did that because I'm not familiar with A squared. Not something that you see very often. Acceleration time squared. So I broke it up this way. Now, when I do break it up that way, I recognize something. Hopefully, you recognize mass times acceleration, and so when I see mass times acceleration, of course, I think about uh, force because of um, Newton's second law. And now, now I'm starting to think differently. Now I'm starting to uh, see um, see the meaning behind the original equation that they gave. So I split it apart because I saw a squared, and I'm not familiar with that. But then it reveals mass times acceleration. I'm familiar with that. Then I have acceleration times time. What is acceleration times time equal to? That's that's correct. Acceleration times time is equal to velocity. We'll say velocity. It's a little bit better than saying speed because it is still a vector, but you're right. Numerically, it would be speed. So so we just converted ma squared times time to force times velocity. Does anybody know what force times velocity is equal to? It's okay. It's okay. Even if you didn't know what force times velocity is equal to, because that's a memory thing. Um, let's try something else. We have force times velocity. Well, force times velocity is force um, times uh, distance over time, because velocity is distance over time. So now we have force times distance over time, and force times distance is exactly, it's work. Force times distance is work. So we have work divided by time. And what is work over time? Yeah. So work over time is power. And power is a watt or a joule per second. So the answer is B. So um, this this is a dimensional analysis. So you see, what did you need to have memorized? Well, you needed to know Newton's second law. Okay. You needed to know that work is force distance and what the units are for work, power, and that's it. Um, V is equal to acceleration times time. You can do this many different ways. The question is, how is V equal to acceleration times time? You can do it many different ways. One way is by just looking at the units. The units for acceleration is meter per second uh, squared. So, and that's time seconds. And so that the second, 1 second would cancel um, from the numerator denominator, so that's equal to meters per second. So that's why acceleration times time is equal to velocity, which is meters per second. But also in our equations that we looked at, whatever, is that acceleration is equal, uh, acceleration is equal to v over t. That was one of the equations that we looked at. And so thus, uh, A T is equal to. So those are different ways you can work it out. Okay, so I hope this shows you that you can have a very, very basic understanding of basic rules, but they can still slam you to see whether or not you really understand dimensional analysis or the relationship between equations and ideas, because this is the big thing. You give a man a fish, he has food for a day. You teach a man a fish, and he has food for a lifetime. And the preparing for the GAMSAT is not about knowing what question is going to be on the test. It's learning the type of reasoning that is required for the exam. Okay, so that was the warm-up. Here's the main meal. So one more question and we're done for today. Okay, so we do have some good answers, and that's great. So yeah, so most of the new book is revision for the 3 sections of the exam. But there are 1,000 practice questions. Most of the practice questions for the book are online, but some of the practice questions, perhaps a third, are in the book, in the new book, and 2/3 of the practice questions are online. But most of the book is revision. So this is the practice question from from the book, and so this idea does come up on the exam from time to time. So we're doing it here. And so first of all, let's see what it, so it says that the force is equal to that equation. So they're presenting a new equation to us, and we have to adapt based on that, and that is the force. So what is force? We know that force is equal to mass times acceleration. Okay, so F is equal to, sorry, F is equal to mass times acceleration, and the mass in SI units is kilograms. So we know that kilogram meter per second squared. And now we need to put this into the fundamental units that they are describing to us. So the fundamental unit of a kilogram in what they are describing to us is mass, right? So, and then the fundamental unit for meters, we have to convert into length because meters is length. And then the fundamental unit for seconds squared, seconds is time, so we convert that into time squared. So on the spot, we are making these um, different conversions, and we know that force is equal to that. Well, now now comes a little logic that you need to apply. And the logic is that because of the equation that we're looking at, I'm not sure why this equation, why this wants to jump around, but because of the equation that we are looking at, this one here, force is equal to this plus this. So here's the logic that you must apply. The logic that you must apply is that because this is the force, and it is equal to this plus this, this is like talking about adding apples to oranges. You can't add apples to oranges unless you're talking about fruit. But, technically, these are two different units, so you can't add them to each other. But if you can add two things to each other, if you can add this whole thing, at-1, plus b, it means that this is equivalent in units to this, and that's why you can add it and make this. So if this is in Newton, which is a kilogram meter per second squared, that means this whole thing must be in the same equivalent unit, and this whole thing must be in the same equivalent unit. This is the logic necessary to solve the rest of it. So we made the conversion because force is mass times acceleration, mass is kilograms, acceleration is meter per second squared, mass is m in the units that we're given, in the system that we're given, length is meters, and time squared is seconds squared. So now let's move to the equivalent part. Oops, all right. Okay, now we're going to use the equivalence for that first part. The first part is A equals, oops, A divided by time. Now I hope everybody can see what I did here. First, um, this first term, a t to the negative 1, it's t to the negative 1 means it's a divided by t, time. So I'm converting time, t, to the new time, t, with the capital letter T. And it's t to the negative 1, which means that it's a divided by t. So I just put a divided by t. That's all I did. And these two terms are equivalent for the reasons that I described already. Now, to determine what a is, all I have to do is multiply both sides by t, and that would isolate a. Another way of thinking of it is if I want to cross out t in the denominator on the right side, I need to cross out one t in the denominator on the left side. You can think of it either way, and you get to the same solution. Okay, so A is done. Next, we need to work out B. Again, that term with B must be equivalent to force, because we're adding apples and apples, or we're adding oranges and oranges. So they must be equivalent in terms of their units. So for B, we get B, and I'm going to convert the small t for time to the big T, which is the units that we're working with now. Okay, so now it's just math. To isolate B on the right-hand side, I'll need to divide both sides by t squared. And if I divide both sides by t squared, I'll get t squared times t squared in the denominator of the left side, and t squared times t squared in the denominator will be t to the power of 4. So that, and now we get. So the question is, how can we ignore B when working out A? So F here is in units of newtons. It means that A t to the -1 must be also in units of newtons. And that's why you can add newtons to newtons. So B t squared must be in newtons. B is not in newtons, cannot be. T is not in newtons, cannot be. But this entire thing, dt squared, must be in newtons because it's being added. Just like you add apples to apples, oranges to oranges, it's being added to this other factor, which is must be in newtons. Together they form newtons. So I can isolate this to figure out what A must be because I know this whole thing is in newtons and this whole thing is also in newtons. That's why we can add them together. And so we get the answer is D. Okay, so that's it for today. I hope this was helpful to you. I think that it gives you an idea of the reasoning that you need to do even if you understand the equations. And as you know, we still have the question of the day. We have the forum, the GAMSAT forum, if you have questions or issues that you didn't get resolved. We also have the Facebook pages if you have questions or issues you need to get resolved. And of course, we have the GAMSAT courses coming up. And even if you're not coming to that, I will have time in the different cities. I'll be going through, and that'll be posted on Facebook if you have different questions.